Welcome to Electronic Materials. This video is about Chapter 5. Let me first give you an overview over what we'll do in Chapter 5. Basically, Chapter 5 is about expanding what we learned in Chapter 4 about metals and semiconductors. And so we will learn that we can use the density of states and the Fermi-Dirac function to calculate the electron density in a conduction band of a semiconductor. We will learn what an intrinsic semiconductor is. It's basically just a pure semiconductor material where electron and hole pairs are generated thermally. Then we'll move on to extrinsic semiconductors, where we will add impurities to this material. And for example, if one puts arsenic into silicon, arsenic has 5 electrons, silicon has only 4 electrons. That means there is 1 electron too many, and that allows to generate additional electrons in the conduction band. So this is a great way to tune the conductivity of semiconductor materials. So extrinsic semiconductors, very important for semiconductor devices. Then we will study the temperature dependence of conductivity of semiconductor materials, and we will find that the conductivity strongly depends on the number of charge carriers that are present in a semiconductor depending on the temperature. A secondary influence on the conductivity is the change of the mobility that also depends on the temperature. And finally, at the end of the chapter, we will look into optical absorption. And here we will find that the attenuation of light through a semiconductor material, or in general through a material, depends on an exponential function which is called the Lambert-Beer's law. Let's first flash back to Chapter 4 when I discussed silicon. If you remember, silicon atoms, they have 4 valence electrons, and they are in 3s and 3p. And when silicon forms a crystal, then these 4 electrons, or these orbitals, the 3s and 3p orbitals, they form so-called sp3 hybrid orbitals, so that they're all the same. And then silicon can form these tetrahedral bonding structures that give it the FCC crystal. And when the bonds happen, we get, as you remember, bonding and anti-bonding orbitals, and then in a crystal, the anti-bonding, they become the conduction band, and the bonding ones become the valence band. And in the semiconductor, the valence band is full with electrons and the conduction band is empty. Another important point about semiconductors is that the conduction band and the valence band are separated by the energy gap, which in silicon is 1.1 electron volt. And that means that silicon is only transparent for infrared light, but for visible light it is opaque. And that you can see here, where the colors of the visible light spectrum are correlated with the photon energies. And so red, which is the lowest energy light that the human eye can see, that has 1.6 electron volts approximately, which is above 1.1 electron volt. So in the rest of this chapter, we will essentially use silicon as the prime example, and it is the basis for most of the discussion that is to follow now. And since it is difficult to draw tetrahedrons, I will use this here to represent these tetrahedrons on the following slides. Let's start out with a silicon crystal at temperature 0. At temperature 0, of course, all the electrons are in the valence band. None of them have any energy to make it across the energy gap. So that means the conduction band is completely empty. The Fermi-Dirac function is a step function. We saw that in Chapter 4. Correspondingly, in the crystal picture, this means that all the electrons are in their bonding orbitals between the silicon atoms. How can we get some electrons into the conduction band? Well, you know that already. Essentially, we turn on the heat. At temperatures that are larger than 0, the Fermi-Dirac function smoothens out, and that means we get some probability to find electrons up here in the conduction band. You can see over here in the crystal picture what this process means for the silicon crystal. Essentially, every time an electron gets elevated into the conduction band, it breaks a bond between two silicon atoms because one of the electrons from a bonding orbital has gone missing. That means that the silicon atom where the electron has gone missing from is now positively charged, and we can look at this as a positive charge that is in the valence band. These positive charges are called holes, and we will see later on that they can move about in the valence band and contribute to the current that is flowing through a semiconductor. What else can we do to get electrons into the conduction band? Well, of course, we can absorb light in the silicon crystal. If the light has an energy that is larger than the band gap, then electrons can be excited from the valence band into the conduction band. If the photon energy is larger than the band gap, then the electrons will end up on some empty state a little bit higher up in the conduction band, and after a very short while they will lose their energy and fall down to the conduction band minimum, EC. That's called thermalization, so these electrons are thermalized. After they sit here for a while at the conduction band minimum, they can recombine with a hole if they find one, and that causes the emission of a photon that has the energy of the band gap. Over here in the crystal picture you can see what such a journey might look like. So the photon that has an energy larger than the band gap hits a bond of the silicon crystal. It liberates the electron into the conduction band. A hole is left behind. The electron is hot, right? It has this energy now above the conduction band minimum. And then as it travels through the crystal, it passes its energy on to the crystal atoms, only to continue to move about at lower energy until it comes close to a hole, and then it can recombine, and that photon with the energy of the band gap is being emitted. Now once we have electrons in the conduction band and holes in the valence band, we can pass a current through the semiconductor. It has become conductive. That we see here schematically. There is a potential now across the semiconductor. Electrons will move downhill and the holes will move in the opposite direction. So we can think of it as a current density that has two components. One is the electron current and the other is the hole current, with P being the hole density and N being the electron density. In an intrinsic semiconductor, of course, if every electron leaves a hole behind in the valence band, it means that N and P are the same. So what does it mean when we have this hole current? You see that here in the crystal picture. Since holes are broken bonds, if a hole wants to move, it essentially means that rather an electron moves onto the hole and leaves a hole behind where it came from. So essentially a broken bond is moving through the crystal in the opposite direction of the electrons in the conduction band. But it's more convenient for calculations to view this process as a positive charge moving in the opposite direction of the electrons in the conduction band. I just told you that the current density in semiconductors is composed of the electron and the hole components of the current. And with that, of course, we can define drift velocities and mobilities for electron and hole currents, and then we can calculate the conductivity of semiconductors. So in the very same way like in chapter 2, when we did it for metals, we can define the drift velocity of the electron current as the electron mobility times the electrical field throughout the crystal, with the mobility being the electron charge times the mean free time of the electrons divided by the effective mass of the electron. If you recall from chapter 4, the effective mass simply takes into account all the effects of the crystal on the mobility of the electrons. And that's an easy way to account for this, because we simply get a factor here that changes the mass. Now we can do exactly the same for the hole current. So we get the drift velocity for the holes with the mobility for the holes. And here for the mobility we have the mean free time for holes and their effective mass. And with this we can define the conductivity of semiconductors, which is just the sum of the electron term and the hole term. I know that at this point you're probably itching to know how to calculate the electron and hole densities. So let's take a flashback to chapter 4, where we did this already for the conduction bands of metals. That's what you see here. We started out by calculating the density of states of the conduction band, and we found that the density G of E is proportional to the square root over the energy. And when we multiply that with the Fermi-Dirac function, then we end up with the number of electrons per unit energy and unit volume. That's the blue curve here. And if we integrate this here from the bottom of the band to the top of the band, then we get the area here, which is just the electron density in that band. So you see that down here. Let's apply this approach to semiconductors now. Here you see the valence and conduction band of the semiconductor with thermally generated electrons and holes. And up here, of course, for the conduction band, everything looks pretty much identical to what we just saw from metals. We have a square root shaped density of states. We have the Fermi-Dirac function for electrons. And then we multiply and we get the number of electrons per volume and energy, and the area here is again the number of electrons per volume, the electron density. The integral looks a little bit different because we're now not integrating from 0 to the top of the band. We are integrating from the bottom of the conduction band EC to the top of the band, but the rest looks identical to the situation in the metal that we just saw on the previous slide. We simply multiply the density with the Fermi-Dirac function and then take the integral to get the density of electrons. Now when we look at the valence band with the holes, things are very similar but mirrored. So we also get a square root dependent density of states. When it comes to the Fermi-Dirac function for holes, it is 1 minus the Fermi-Dirac function of electrons. And that makes a lot of sense because the probability to either find a hole or an electron at a given energy should always be 1. And from then on, everything is the same. We simply multiply again the density of states with the Fermi-Dirac function, and we take the integral from the bottom of the band to the valence band maximum, EV, and then we get the hole density in that band. The final step on the path to get the electron density is to calculate this integral that we just developed on the previous slide. And so the approach is pretty much identical to what I did in chapter 4 for metals, but because the conduction band minimum EC is pretty far away from the Fermi energy, we can actually approximate the Fermi-Dirac function with a simple exponential function here where it counts for our integral. And so we can say that the Fermi-Dirac function is approximated by an exponential function that just has the difference between the energy and the Fermi energy divided by kT in it. When it comes to the density of states, GE, we get the same square root like we got it for metals, But the curve is now, of course, shifted to the conduction band minimum, and so we have here E minus EC under the square root. But the factor is exactly the same. It contains the effective mass of the electron. So now we plug in these two expressions under the integral, and we pull out that constant in front of the integral, and now we need to evaluate this integral here. Integration of this integral yields this term here, and if you look at it, we have here the exponential function of the difference between the conduction band minimum and the Fermi energy divided by kT. So this is essentially the probability for finding an electron here at that EC point, and that is multiplied with a constant, and this constant we can regard as the effective density of states at EC NC. So this means we are replacing evaluation of this integral by simply multiplying a constant density of states with the probability to find an electron at that energy, and that gives us the density of the electrons. It's interesting to wonder why we are getting such a simple and fairly elegant result for the electron density. Well, if you look at it, it makes a lot of sense that we are only considering a constant density of states here at the bottom of the conduction band, because we are pretty far away from the Fermi energy, and that means that we only have a few electrons up here in the first place, and that means they are all at the conduction band minimum. And so we don't really have to consider all that complexity of the density of states. We can say, well, the electrons are all at the conduction band minimum, and there we have a certain density of states where these electrons are on, and the probability to find an electron on these states simply depends on how close we are to the Fermi energy. And therefore, this is all we have to do in order to get a pretty good estimate or approximation for the electron density in the conduction band of a semiconductor. You probably guessed it, for holes we can do exactly the same approach. So what we get for holes is a very similar expression, except that under the exponential function we have now the difference between the valence band maximum and the Fermi energy, and in the effective density of state we have the effective mass of the holes. It's interesting to see what happens when we multiply the electron and hole densities. So if we calculate this expression, then we get the effective densities of states multiplied times an exponential function that has just the difference between the conduction band minimum and the valence band maximum in it, which is of course the band gap. So we can say n times p is the effective densities of states multiplied with the exponential function of minus the band gap divided by kT. And this here is of course a constant that depends on a particular material. So each material has a certain value for n times p, and therefore we introduce here Ni, which is called the intrinsic carrier concentration, which is a constant at a given temperature. For silicon, for example, Ni is 1.45 times 10 to the minus 10 per cubic centimeter. So all semiconductors have a different Ni depending on their band gap and depending on the effective densities of states that they have. So this relationship, n times p equals the intrinsic carrier concentration squared, that's called the mass action law. And we will see later on in 5.2, the chapter about extrinsic semiconductors, when we change n and p by doping, that this is still valid even if we change the concentration of N or P. So that means if you make N larger, then correspondingly P needs to get smaller in order to maintain this constant value. I said earlier that the Fermi energy is in the center of the band gap. Well, there's a way to demonstrate that this is really the case. So we know that in an intrinsic semiconductor, N equals P because each electron has a corresponding hole in the valence band. So when we start out with N equals P, and we just put in the expressions now for the electron and hole densities that we developed on the previous slides, and do a little bit of math here. So here we take the logarithm, and that liberates the exponents of the exponential functions, and so we can sort them on one side, and then you see that what's left here is just the band gap, and we get this expression here where we have the effective densities of states in the valence band divided by the effective density of states in the conduction band under a logarithm, and this here is 1 if these two are the same. So this is the assumption here that the effective densities of states are the same. But if we do that, then we see here that the Fermi energy of the intrinsic material is just EV plus half of the band gap. And so indeed, the Fermi energy is in the center of the band gap if the effective densities of states are the same. And so in many semiconductors, this is actually pretty close. And so it's a pretty good assumption that the Fermi energy is close to the center of the gap in many semiconductor materials. The previous subchapter about intrinsic semiconductors dealt with the pure semiconductor material, so ideally no impurities, no defects, etc. And then in that case, all the electrons in the conduction band came from the thermal excitation across the band gap. Now, there's a way to change the number of carriers in the conduction band or also the valence band by introducing impurities into the material. And with this, we can control N or P and create a situation where N is not equal P anymore, like in the intrinsic material. There are two types of extrinsic semiconductors. We call them N-type when we have more electrons than holes, and we call them P-type when we have more holes than electrons. So on this slide here, let's start out with N-type semiconductors where we make N larger than P, and this is done by introducing impurities into the silicon matrix that have more electrons than silicon. So a prime example for N-type semiconductors is arsenic. And arsenic, when you look here at the snippet of the periodic system, arsenic has 5 valence electrons, and so there is sort of one too many if we put an arsenic into the silicon lattice. So 4 of these electrons will enter bonds with the surrounding silicon atoms and make a tetrahedron like all the other atoms here, but the 5th electron is a little bit lost in space here, and so it takes only very little energy to liberate it into the conduction band. And so when we look here at the band diagram, the arsenic ions, they are just 0.03 electron volts below the conduction band minimum EC, and if you remember that Kt at room temperature is 0.026 electron volts, that's very close to 0.03. That means that most of these arsenic atoms in the silicon crystal will be ionized, will have given their electrons into the conduction band at room temperature. That means, one for one, each of these arsenic atoms that one can implant into the silicon wafer will give their electron into the conduction band. And so this is a phenomenal way to control the conductivity of a semiconductor material by simply putting a certain amount of arsenic in a well-controlled manner into the silicon wafer. And with that we can adjust the conductivity. Now, consequence of doing so is of course that the Fermi energy is shifting towards the conduction band. The reason for that is that we have now much more electrons up here than we have holes down here, and that means we need to adjust the curve that we get larger probabilities to find an electron on a conduction band state here compared to the probability of not finding one down here. You probably just wondered, why is it only 0.03 electron volts to get this electron away from the arsenic atom inside the silicon crystal? You probably remembered that the ionization energy of a hydrogen atom was 13.6 electron volts, so you would expect that arsenic would have a similar ionization energy that is at least a few electron volts. And when you look it up, you will actually find that the ionization energy of an isolated arsenic atom in vacuum is 9.82 electron volts. So how do we get from this almost 10 electron volts to 0.03 to get this electron away from the arsenic just because it's inside the silicon lattice? Now, the reason for this difference is the presence of all these other electrons around the arsenic. So when the electron leaves the arsenic atom, then these electrons here shield or screen, as they say, the positive charge that is left behind on the arsenic. And that makes the Coulomb potential curve much flatter than compared to the case in vacuum. And with that, we get a much smaller ionization energy of that arsenic atom within the crystal. If we look here at the formula to calculate the ionization energy of the hydrogen atom, where we have the electron mass and the permittivity of vacuum, these are the two items that change when we go inside the crystal, when we put the arsenic atom inside the crystal. First of all, we exchange the electron mass with the effective electron mass, which, if you remember, incorporates the influence of all the other things that are around the electron inside the crystal. So here, when we look it up, the effective mass is about 1/3 of the electron mass in vacuum. And if we look at the permittivity, inside the crystal, we have to multiply the permittivity in vacuum with the relative permittivity ER, and that is 11.9 for silicon. And since it's squared in this formula, we get actually a factor 100 right there. And so that explains how we can get from 13, or rather from 9.82 to 0.03, right? Here we get a factor 3, and then here a factor 100 almost. And so that explains why the energy requirement is so much lower, and why simple thermal energy kT is enough to get this electron from the arsenic into the conduction band. Now, how about p doping? As usual, when it comes to holes, the process is very similar to what we learn about the electrons. Here now we need to select an impurity that has one electron too few, and a very popular dopant for p-type doping of silicon is boron, which has 3 electrons compared to the 4 of silicon. So when we integrate boron into the silicon matrix, we have a situation where the boron can make 3 successful bonds with the surrounding silicon atoms, while it draws a blank here with the 4th one because it doesn't have an electron. So putting a boron into the silicon matrix introduces a hole. And then electrons from other bonds here between silicon atoms can hop onto this hole, and we can get that hole conduction mechanism in the valence band. Like in the case of n-type doping, the Fermi energy shifts. In this case, of course, it shifts downwards because now we have to arrange for a larger probability to find a hole on states in the valence band. How much energy does it take to get an electron onto the boron? Well, in this case it's 0.05 electron volts, so it's a little bit more than in the case of the arsenic ionization, but still it's very close to kT, so most of these boron atoms will contain an electron at room temperature, and so that generates 1-for-1 a hole in the valence band. I just told you that at room temperature most of these donors or acceptors are ionized in a semiconductor because it takes so little energy to liberate the electron from a donor or to capture an electron onto an acceptor. But it's interesting to look into how does this ionization process of either one depend on the temperature. These two functions here give the probability that the ionization is happening. And so we have one here for the donors and one here for the acceptors. And of course these look very similar. They look very similar to the Fermi-Dirac function, but they have these factors here before the exponential function. And these factors, they come from the fact that here we have now isolated atoms within the crystal. So that means that the states are not states in a band, but rather atomic states that need to be populated with a certain electron spin. And because of that, the probabilities change. And so it turns out, for various reasons, that for donors there's typically a factor 1/2 before the exponential function, and for acceptors it is typically a factor 1/4. These factors are called degeneracy factors. So at this point you understand how we can change the number of holes or electrons in a semiconductor material. An interesting question in this context is what happens to the other type of charge carrier. So in the example of an N-type material, we have many more electrons now up here than we had before just from thermal generation. And this large number of electrons, that causes a much higher probability for recombination with the holes that are in the valence band. Now the number of holes here originally would still be the same like in an intrinsic material, because the dopants here only affect the density of electrons in the conduction band. But because we have so many electrons up here now, the increased recombination reduces the number of holes dramatically in the valence band. And we can calculate this because the mass action law still applies. So for the case of an N-type material, we have now P times the donor concentration, because at room temperature they are mostly ionized. We can replace N with ND, and that must still be equal of the intrinsic carrier concentration squared. In the P-type material, we have N times the acceptor density, which is equal to the intrinsic carrier density squared. Let's do an example. A silicon wafer is N-doped with 2 times 10 to the 17 arsenic atoms per cubic centimeter. And so let's calculate now the concentration of holes that we have in there. If it's at room temperature, then we can assume that all donors are ionized. So we have basically 2 times 10 to the 17 per cubic centimeter electron concentration in there. So all we have to do now to calculate P is to solve the mass action law for P and plug in the carrier concentration of intrinsic silicon, which is 1.45 times 10 to the 10 squared, and divide by that electron concentration. And when we do that division, we find that we have about 1000 holes per cubic centimeter in this N-type silicon wafer. So if you compare 10 to the 3 to 10 to the 17, you see that there is a difference of 14 magnitudes in the number of electrons and the number of holes that we have in this material. Also, it is clear that the number of holes has taken a severe hit compared to the intrinsic number of holes, which would have been 10 to the 10. So there's also 7 magnitudes difference. So it's pretty clear that the holes in this n-type material don't play much of a role for conductivity anymore, and that all the action is in the conduction band. Of course, in a p-type material we would see the opposite. We would have mainly holes that do the conducting, while the electrons would be severely diminished in a very similar way like the holes here. And that's the reason why we call the electrons in an n-type material majority carriers and the holes minority carriers, and of course vice versa in a p-type material. With this in mind, we can calculate the conductivity of an extrinsic semiconductor material. If you remember, the conductivity of a semiconductor is just the conductivities related to electrons plus the conductivity related to holes. But since we just learned that the majority carriers are dominant and the minority carriers do not bring much to the table in an extrinsic semiconductor material, it is not surprising that we can say that the conductivity of an n-type material is essentially the electron-based conductivity. So we just have E times the donor concentration times the electron mobility. And correspondingly in a p-type material, we are just left with the whole conductivity terms E times the acceptor concentration times the whole mobility. Another interesting question to answer about extrinsic semiconductors is, where is the Fermi energy if we dope a material? As I told you earlier, that when we dope a semiconductor, the Fermi energy is shifting towards one of the band edges depending on the doping type. So here, as shown in this flashback to an earlier slide, for the case of a p-type material, the Fermi energy is moving towards the top of the valence band in order to account for the added hole density that we have down here in the valence band. In the case of an n-type material, the Fermi energy would shift towards the conduction band minimum. So how can we calculate this new Fermi energy for the doped material? Well, if you recall earlier, we calculated the intrinsic carrier density by multiplying the effective density of states with the exponential function of this difference between the intrinsic Fermi energy and the conduction band minimum divided by kT. So this formula here relates the Fermi energy to the carrier density. This formula also applies for doped materials, except now that we have the dopant density and the Fermi level of the extrinsic material, the extrinsic Fermi level. And so it turns out if we divide these two, so if we calculate Nd divided by the intrinsic carrier density, then we get the exponential function of the difference between the extrinsic and the intrinsic Fermi levels. So by taking the logarithm of this equation, we liberate that difference, and we can say that the difference of the Fermi levels is just kT times the logarithm of the donor density divided by the intrinsic carrier density. Let's do an example for silicon at 300 Kelvin room temperature with a donor density of 10 to the 16. So if we plug in the numbers here, we calculate 0.348 electron volts. This result means that the Fermi energy now is between the center of the gap and the band edge. It's interesting to figure out how much doping do we need to do in order to get the Fermi energy close to a band edge, and that's why I went over to Wolfram Alpha and did a log linear plot of this equation. And so that's what you see here. On the x-axis we have the donor density, and that's now the log scale, right? So here's 10 to the 12, 14, 16, 10 to the 18, and this here is the energy difference between the actual Fermi level and the intrinsic Fermi level, so basically what we just calculated here. And so you see here that if we go to a doping density of higher than 10 to the 18, the curve takes us very close to the conduction band minimum, right? This here is 0.5, and here we have about 0.55, which is just half of the gap of silicon. So Doping densities that are higher than 10 to the 18 get the Fermi level close to the band edge. Let's move on to subchapter 5.3, temperature dependence of conductivity in semiconductors. You already know that conductivity depends on the carrier density and the mobility of those carriers, and in the case of semiconductors for electrons and for the holes. And you also know that both of these factors are temperature dependent. So if we want to talk about the conductivity temperature dependence in a semiconductor, we need to look into the temperature dependence of the carrier density and the temperature dependence of the mobility. On the next few slides, we will examine these two temperature dependencies, and we will find that we will get three temperature ranges for the temperature dependence of the carrier concentrations: a low temperature range where not all of the dopants are ionized, a medium temperature range where they are all ionized, and then a high temperature range where the thermal generation of charge carriers becomes dominant. And so this will give us this red curve. And then we will look into the temperature dependence of the mobilities, and there we will see that there are basically two temperature ranges, where at high temperatures the lattice vibrations dominate the mobility, while at low temperature the mobility is mainly determined by impurity-based scattering, and so that will give us that green curve. And when we throw both of the red and the green curves together, then we'll get the temperature dependence of the conductivity, which is the purple curve here. Let's discuss the carrier concentration temperature dependence first. And I'm going to do this at the example of an N-type semiconductor. The discussion of P-type materials would yield exactly the same conclusions, so it's enough if we just do this here now at the example of an N-type material. As I just said, there are three temperature ranges when it comes to carrier concentration temperature dependence. At low temperatures, the so-called ionization range, not all of the donors are ionized, and so as the temperature goes up, more and more electrons make it into the conduction band, and then at some point all the donors are ionized. And at that point we go into the medium temperature range, which is called the extrinsic range. So this is the situation that we assumed on all the previous slides about the extrinsic semiconductor. That's when all of the donors are ionized and we have essentially a constant electron concentration in the conduction band. If we go to even higher temperatures, then we hit the intrinsic range, and it's called intrinsic range because the semiconductor is essentially becoming an intrinsic material, because at some point when the temperature is high enough, the thermally generated electrons in the conduction band outnumber the electrons that originate from the donors. So we go from ionization of the donors to having the donors completely ionized, but thermal generation is not important yet, and then at some temperature the thermal generation takes over and dominates the material. It's interesting to look what's happening with the Fermi level through these three ranges. In the intrinsic range, of course, the Fermi energy will near again the center of the gap, because once the thermal generation dominates, we have a similar number of electrons up here like we have holes down here, and then the Fermi energy is again in the center of the energy gap. In the extrinsic range, the Fermi energy is somewhere in between the intrinsic Fermi energy and the conduction band minimum EC. And in the low temperature range, the Fermi level is actually in between the donor energy level ED and the bottom of the conduction band EC. When we look at the formulas for the electron density in the conduction band, then we have here this expression. It's very similar to the formula that we found for the intrinsic semiconductor materials, except that this here is governed by the Fermi-Dirac function for impurities, and so we get this factor 1/2. Also, the band gap is replaced by the gap between the conduction band minimum and the donor energy level. In a way, this is sort of making its own intrinsic semiconductor here between the ED and EC levels, with ED acting as the valence band, because we have thermal generation across this little gap here between ED and EC. As I just said, in the extrinsic range, the carrier concentration is constant, so the electron density is just the dopant density, because all of the dopants are ionized. And at the high temperature intrinsic range, we have essentially the formula for intrinsic semiconductors. This graph summarizes what I just discussed on the previous slide. So here we have the three temperature ranges. Note that over here we have the low temperature and over here the high temperature range. Also, this is a logarithm versus 1 over t plot. And when we do that, then we get actually straight lines here, and the slopes are just the factors under the exponential function before the 1 over t that is in there. And what we see here is at the low temperature range, we have a slope that is defined by the gap between the bottom of the conduction band and the donor level, divided by 2 times the Boltzmann constant. And so we walk up here as the temperature increases and the donors get more and more ionized, and then at some point they're all ionized and we enter the extrinsic range where the carrier concentration is constant. And then once we reach a temperature that's high enough that a significant number of electrons can make it across the band gap, then we enter the intrinsic range, and that has a slope that is defined by the band gap divided by 2 times the Boltzmann constant. So we have this behavior across the entire temperature range. Now let's discuss the drift mobility temperature dependence, and I'll focus first on the high temperature range, which is the lattice scattering dependent mobility. If you remember from chapter 2, the mobility depends on the mean free time between collisions of the electrons with the atoms of the crystal. And so calculating the mobility just involves getting an expression for the mean free time, dividing by the effective mass of the electron and multiplying with the electron charge. You already know this figure here from chapter 2, where we calculated the mobility for metals. And we found back then that the mean free time was just 1 divided by the scattering cross-section times the velocity of the electrons and multiplied with the number of scatterers. So in metals, the velocity of the electrons was assumed to be constant with temperature, but in semiconductors this is different. Why is it constant in metals? Well, the reason for that is that the electrons that participate in conductivity, they are close to the Fermi energy, and the Fermi energy is already a pretty sizable chunk of energy relative to the ground state of the electrons at the bottom of the bands. And that means that additional energy that comes from temperature changes is pretty insignificant in comparison to the total energy that the electrons already have. So in practical terms, this means the velocity of metal electrons is just higher than the velocity of semiconductor electrons, because in metals the electrons already have this chunk of energy because they are at the Fermi energy. In semiconductors it's different because the electrons that participate in conductivity are at the bottom of the conduction band, and that means they have very little energy except that they get from the temperature. And so that means that the velocity of the electrons in semiconductors is essentially 3/2 kT, or proportional to 3½ kT, their thermal energy, while in metals it is the Fermi energy plus 3½ kT, and 3½ kT is much smaller than EF. And that means here in metals the velocity can be regarded as pretty much as constant, while in semiconductor it will vary fairly strongly with the temperature. So that is the main change between what we did for metals and what we do now for semiconductors. We'll replace this constant speed u in metals with the thermal velocity in semiconductors. Now, how do we calculate this thermal velocity? Well, we just equate 3½ kT with 1/2 mv squared, and then we solve for the velocity, and so we find that the velocity is proportional to the square root of the temperature. So now we know the temperature dependence of the velocity. The remaining factor is the cross-section, and here of course nothing changed in comparison to metals. The atoms still vibrate, and the area that they occupy depending on the temperature, that varies proportional to the temperature. And so in total here, when it comes to the mean free time, when it comes to its temperature dependence, we find that we have a temperature dependence that is T to the minus 3/2. And that gives us the lattice vibration scattering limited mobility temperature dependence, which is basically the same. Let's move on to the lower temperature range. At lower temperatures, like in metals, the drift mobility is limited by impurity scattering. Now, impurity scattering is different from scattering on lattice atoms because the impurities are ionized, and so they have a charge, a positive charge. And that means the electrons that come by here, they see a Coulomb potential. And depending on the velocity of these electrons, they are either captured or deflected by this Coulomb potential, so they make a slingshot around the impurity and get scattered, or if they have enough energy, they can continue on their straight path or just suffer a small deflection. We can define a critical radius here that depends on the thermal velocity of the electrons. The faster these electrons are, the closer they can get to the positively charged impurity and still get away. And so by equating the thermal energy of the electrons and the potential energy depending on the radius, we can calculate that critical radius for a given temperature. So this critical radius now is, of course, defining the size of the impurity for scattering purposes, and so the scattering cross-section is just pi times RC squared, and with that we get a temperature dependence of the cross-section that is 1 divided by T squared. So we can plug this into the mean free time and use the temperature dependence of the thermal velocity that we determined on the previous slide. And with that we get a temperature dependence of T to the 3/2. That of course carries through to the mobility. Note that we have to divide here by the impurity concentration because of course all this depends on how many impurities are in the semiconductor in the first place. So let me summarize. We know now that the impurity limited mobility is proportional to T to the 3/2, and the lattice limited mobility term is proportional to T to the minus 3/2. So the total mobility would be calculated by adding the reciprocals and then taking the reciprocal of that. So let's see how this holds up with the experiment. In this graph here, you see the drift mobilities plotted of germanium depending on the temperature. The curves here differ in that they were measured on germanium with different impurity content. So down here, this is the one with the highest impurity content, and up here we have this purple one that is the lowest impurity content. It's interesting to note that this here is a log-log graph, so we have here the logarithm of the temperature and here the logarithm of the electron drift mobility. And that means that if we have a function like this here where we have an exponent, then this exponent shows up as the slope of the curve in such a log-log graph. There's an interesting Wikipedia entry about this if you're interested. So this makes it very convenient to read this graph here, because our theoretical limits are now these slopes here. So this is the impurity limited mobility slope, and this here is the lattice vibration limited slope. And so you see here, when we have a high concentration of impurities, as the temperature goes from low to high, we are going from a slope that is close to this here to a slope that is close to this here. So you see clearly how the influence of the impurities wanes as we go to higher temperatures and the lattice vibrations take over. You also see that when we go to material with very low concentrations of impurities, then the lattice limited mobility dominates. We get a very similar slope here in this germanium sample with a low concentration. Now we can finally put it all together. Let's remember, conductivity is just the carrier densities multiplied with the mobilities for electrons and holes. And so these two curves that we just determined, one for the carrier density and one for the mobility, if we multiply these two curves, then we get the temperature dependence of the conductivity. And so we see here that the conductivity of a semiconductor is high at high temperatures and low at low temperatures. And we get this bulge here that comes from the temperature dependence of the mobility. Let's compare this result with what we learned earlier about metals. On this graph here, the resistivity is plotted versus the temperature, and please note that the temperature here is on a regular scale, where low temperatures are here and high temperatures are out here. This one here is different. And also here we have the conductivity and here we have the resistivity. But if we compare now the resistivity of metals with that of semiconductors, we see that the resistivity of metals goes up with the temperature, while the resistivity of semiconductors goes down. And the main difference for this behavior is that in metals we have a constant number of carriers, because it's just the electrons in the electron gas. All the valence electrons participate. They are in the conduction band, while in semiconductors the number of electrons in the conduction band strongly depends on the temperature, because at low temperatures we first ionize all the donors, and then at high temperatures we get even more carriers, because we start to excite electrons from the valence band into the conduction band. And so as the temperature increases, we get more and more electrons into the conduction band, and that of course strongly increases the conductivity, so the resistivity goes down. In metals, the only thing that inhibits the current that increases the resistivity as the temperature increases is essentially the lattice vibration limited mobility. So the atoms vibrate more, the cross-section gets bigger, and so we get more scattering, and that reduces the mobility, and that's why in metals the resistivity goes up with the temperature. In semiconductors, this phenomenon is compensated because we get more and more carriers, and so the mobility doesn't play such a big role here, and this is why we get this opposite behavior. There is actually a way to turn semiconductors in a material that behaves like a metal when it comes to the conductivity temperature dependence. Such semiconductors are called degenerate. And the difference to a normal semiconductor is that in a degenerate semiconductor we have so many impurities in it that the Fermi energy is inside the conduction band. And of course you recognize, if we have a situation like this looks a lot like a metal, right? Because we have the Fermi level inside the band and the states are filled up to the Fermi level. And that means we cannot use that approximation anymore that we used for calculating the electron density, where we replaced the Fermi-Dirac function with the Boltzmann statistics and just used the exponential term and forgot about the 1 divided by 1 plus exponential term that's in the Fermi-Dirac function. Now here we cannot do this anymore, and so what we get is essentially the same treatment like for metals, and we end up with a conductivity dependence that is proportional to 1 over the temperature. So we have conductivity going down with rising temperatures, and the resistivity goes up when the temperature increases. This type of semiconductor is very useful for making metal semiconductor contacts on semiconductor wafers. I just spent a lot of time talking about what electrons can do when they are in the conduction band, and we know now how they get there by thermal generation. So they get some thermal energy in the valence band, and then they are able to jump up into the conduction band. Once they're there, they usually all go down to the band edge, to the minimum of the conduction band, and they lose that energy via heat generation, so the crystal gets a little warmer. Now when they are at the band edge, then they sort of wait there until they have a reason to lose this energy and go back into the valence band. And of course they can only go back when they find a hole to jump onto to recombine with. And when they do that directly, they do that by emitting a photon. It's interesting to know that only in some select semiconductors this is possible, that they jump directly into the valence band and emit a photon. Such semiconductors are called direct semiconductors. And there, the reason why this works is that electrons and holes, they have the same momentum when they are at the band edges. So you can imagine this as like they are going in the same direction, and so they can meet and interact properly. Now, in some other semiconductors, which are called indirect semiconductors, and silicon and germanium are among those, these photon emissions are not possible. And so there the recombination happens via so-called recombination centers. And these recombination centers are impurities that are in the material or defects that create states in the band gap, and that enables electrons to jump on these states, and then from these states they go on into the valence band. And this usually happens under heat generation. So there are no photons generated, but the material gets a little bit warmer. In addition to recombination centers, there are also so-called trapping centers. These are also states generated by impurities or defects, but they are a little bit closer to the band edges. And these states, they sort of, you can imagine them as a parking space for electrons or holes, where these carriers get captured, and then after a little while they get released back into their band through thermal excitation. And such trapping states, they lead to a reduced conductivity because they affect the mobility and the number of charge carriers that are in the conduction or valence band. Here you see some example of such gap states. This is for silicon, and these here are for gallium arsenide. Gallium arsenide has a band gap of 1.42, silicon of 1.12. And so you see here, depending on what element is doing the impurity in the material, we get states that have different energies relative to the band edges. So gold here would, for example, make a really nice recombination center in silicon. And in gallium arsenide, oxygen makes states that are close to the center of the gap. So it's pretty obvious that impurities need to be controlled tightly in semiconductor manufacturing, because you can imagine if you have a lot of these states here, then the material will have entirely different conductive properties. The final chapter in chapter 5 is optical absorption. And so you know now already that when a photon impinges on a semiconductor with a photon energy that's larger than the band gap, then we get photoelectrons in the conduction band, and these electrons thermalize to the band edge, and there then they have their thermal energy, 3½ kT, with which they can move around and find a hole to recombine with. And if this is a direct semiconductor, then we get a photon emitted that corresponds to the energy of the band gap. Now it's interesting to realize that this absorption process, the efficiency of the absorption process, or the likelihood that this happens when a photon comes through the material, that depends on the density of states in the originating state and the final state onto which the electron jumps in the conduction band. From chapter 4 we know that the density of states is largest at the center of a band, while it is lowest at the band edges. And that means that transitions between the edges have a low probability, while transitions between the centers of the bands, they have a high probability. And that means that the absorption coefficient is larger for energies corresponding to this transition than to transitions that are between the edges of the bands. Let's try to put some numbers to this absorption process. In general, if light is being absorbed in a material, we get an exponential attenuation of the intensity depending on the length of the path through the material. So we can say, if we look at a thin slice of the material that has the thickness delta x, we can say that delta I, the change of the intensity of the light when it goes through that slice, is minus alpha, and alpha is the absorption coefficient, times the intensity with which we go in, multiplied with the thickness of this slice. And if we rearrange this a little bit, then we get this differential equation here. And if you look at it, it's a first order differential equation where the differential is equal to a constant times the function, and that usually has an exponential function as solution. And so we get this formula here that states that the intensity at a certain location x is the original intensity times the exponential function of minus absorption coefficient times the distance the light is going through the material. And this is called the Lambert-Beer law. And with this we could, for example, calculate how much attenuation occurs as the light goes through this piece of material that has a width of w. So you would just plug in w as x, and then you could calculate the intensity of the light that comes out here if you put in I0. Let's have a look at some experimental results where they measured the absorption coefficient of silicon at different temperatures. So in this graph here you see the absorption coefficient plotted versus the photon energy. So basically the experiment works like with a monochromator. Monochromatic light is put through a thin slice of silicon, and the attenuation of the light is measured, and then the absorption coefficient is calculated with the Lambert-Beer's law. And so these are the curves that an experiment like this yields. And so what we see here, let's look first at the red curve. It was measured at room temperature at a photon energy that is equal to the band gap of silicon, 1.12 if you remember. At that photon energy, the absorption coefficient is pretty much 0, and then as the photon energy increases swiftly, the absorption coefficient goes up. And the further we go away from the band edge, the higher the absorption coefficient becomes. And this is a direct demonstration of what I said earlier, that transitions between the band centers are more likely than transitions right at the band edge, and so this is why the absorption coefficient goes up dramatically as we go away from the band edge. Now what is happening here when they measure at 77 Kelvin or at 676 Kelvin? Well, 77 Kelvin is liquid nitrogen temperature, so here they put the slice of silicon into liquid nitrogen and then did the same experiment again. And so you see here that the curve now starts a little bit later on the photon energy scale, maybe at 1.2 electron volt. And that is a direct consequence of the fact that the band gap of a semiconductor material changes with the temperature. When the temperature goes down, then the material shrinks a little bit because the atoms don't vibrate that much anymore. And so they are closer together, and that creates more overlap between the valence orbitals between the atoms, and that means that the bonding and anti-bonding orbitals are further apart, and so the band gap as a result gets a little bit bigger. This is shown here on this graph, which plots the band gap versus the temperature for silicon and gallium arsenide. And the dashed line here, that's the room temperature, 300 Kelvin. And so you see that at lower temperatures, the band gap of silicon goes from 1.12 to 1.17. And that must be this here, 1.17. Gallium arsenide does a similar thing. So this is valid for all semiconductor materials. At low temperatures, the band gap gets large, and at higher temperatures, the band gap gets smaller. And this is why the 676 Kelvin curve looks like it would hit the zero absorption coefficient point at a lower photon energy. And this concludes chapter 5. Thanks for watching.